So it's my pleasure to introduce Sashadhar Dutta, who is from the Higher School of Economics in Moscow. And he's going to be speaking about the reducibility of the Markov equation using Newton polygons. You have 30 minutes, including questions. So it'd be good if we can maybe finish at 5 minutes to 2. Yeah. Okay. You don't know what 5 minutes to 2 is. You have 25 minutes. Yeah. Okay. Thank you.
Oh, okay. So thank you, everyone, for giving me this opportunity to tell my talk. So the main thing is that this topic, the irreducibility of Markov equation using Newton polygon. So there is some motivation regarding that. So this topic right now, the last 2 months, I'm working on it, and I did not publish this paper, but I have some motivation regarding this thing. So the last year I was working on Markov equations, and so um, in that time, okay. So what is the meaning of Markov equation? So Markov equation is an equation looking like that. It was introduced by Andrei Markov in 1879, and it has a lot of applications in their cases. So this year, uh, I was working on my paper, my first paper, and it is also available on archive. It is in preprint in archive. So we were trying to find some reducibility or irreducibility of Fibonacci sequences, etc., by using the Newton polygon. So 2 months ago, I was thinking that what about the Markov equation? How is it reducible or irreducible if we apply the Newton polygon? So I told you that what is the meaning of Markov equation, what is the definition of Markov equation, and um, then I will be telling what is the Newton polygon and how how far what result we get from here. Okay, so the this is the Markov equation. It is the definition of Markov equation, and you know that it has some all of the applications in this respectively field. So continued fractions. So there is a paper written by Michael Rabideau and Ralph Skriflar in 2020. They published the paper. It is available in archive also. So continued fractions and orderings on Markov numbers. So a very interesting paper. Also hyperbolic geometry. It has some applications on there. So then you can see this paper written by Boris Springborn, 2019, and it has a lot of papers on algebraic geometry. So I cannot write exactly one or two paper because it is it is finite, the paper is finite, but a lot of papers are there. Okay, so cluster algebra, one paper in 2025 written by Banyan and Goeda, and representation theory, that Markov equation is not partition regular, written by Tao and Yang, 2025. So now we need to discuss about the why we need to study the Markov equation. So you know that Markov equation is one of the most interesting and the most, you can say, one kind of uh, unsolved problem. Because you cannot find, maybe in the future, because right now this is the age of AI and some interesting tools. In the future, I hope that we mathematicians, we don't need to calculate by ourselves. In the future, maybe we will be getting some good tools to solve all the equations or unsolved equation. Maybe in the future, maybe 2000, 3000 years later, I don't know when. But okay, so this is somehow you cannot find the last triple of Markov equation. So that's why we are trying to improve the triples, or we are trying to find the triples, and a lot of papers we are publishing right now. So you know that it has some integer solutions, because by definition it is written that it has some integer solutions. Also, a lot of mathematicians, they are trying to find some rational points on Markov equations. It is also applicable of geometry of algebraic varieties and irreducibility of associated polynomials, etc., etc. So now I have to tell about the Markov triples. So you can see that is, suppose I'm choosing A, B, C, that is from Z3, Z, and if it satisfies the Markov equation, then this A, B, C is called the Markov triples. So the first Markov triple is 1, 1, 1. Also 0, 0, 0, it is also satisfied. 1, 1, 1, it is also satisfying the proof. And 1, 1, 2, 1, 2, 3, and so on. And then scientists, they are thinking about the generating Markov triples, that how we can generate or how we can connect Markov equations to each other. So so suppose how this is the calculation. So suppose I'm choosing A, B, C. This is a Markov triple. So I'm just replacing this C by C dash, that is equals to 3AB minus C. Okay. So it produces another solution. So you can see this is looking like that. Also for we can change B, and then we get some similar solutions on there. So so it forms a Markov triples. Just you can see that is the infinite graph is called. This is because this is infinite. I mean, you can get a lot of triples or branches up there. So now I'm telling about the algebraic geometric interpretation of Markov equations. So you know that this is the Markov equations, and uh, I'm defining some affine algebraic surface. Okay, so x, y, z belongs to A3 affine algebraic surface. So x square plus y square plus z square equals to 3xy. So this, I mean, I'm just choosing the Markov triples from these affine algebraic surfaces A3. So now the main motivation is that, is it irreducible? What are its rational points? So I mean, few months ago, S.J. Evans from Ludgrove University, UK. So he published a paper on saturation of Markov polynomials. So uh, there he described about the Markov equations on, I mean, rational points on so on, and also he studied a lot of works on this uh, topic. I mean, Markov equations using Newton Polygon and etc. In their paper, they were using a similar method, but my topic is slightly, I mean, different, and these things. So now the basic another definition is that what is the meaning of reducibility and irreducibility. So I'm choosing any polynomial. Okay. So if this polynomial is reducible, I mean, this polynomial we can write into two parts. So also the important thing is that this the degree of okay. So if we can split a polynomial into two more polynomials, into product of two polynomials, so degree of this g, that is greater than 0. Of course, this should be positive and non-negative, and also positive there. And degree of h, that is greater than 0. Otherwise, f is irreducible. So this is called the irreducibility. So this is important tool to prove our results and so on. now why this irreducibility matters. So we need to find the geometry of the curve and some connectedness. I mean, how we can find some other solutions on there. So also some rational points on there, and so on. I mean, that's why. So now, few days ago, I was thinking about that. Okay, Markov equation, that is three triples. So x, y, z. It has x, y, z. So if I can, I mean, convert it to in a, I mean, two variables. I mean, x and y, because I'm transforming from three to two variables. So how I can transform it to? So suppose I'm choosing z, that is equals to alpha x plus beta y. So it is looking like just two variables. It converted into two variables. So just you can see that is how I did. So z equals to alpha x plus beta y. Okay, and I'm just putting the value of x square plus y square plus z square equals to 3xyz. Okay, and so I'm just putting this value in z square. So just here and here, and just separate them and just calculate them. Just simple calculation, and I get this cubic polynomial. So you can see x square, y square, x y, x square y, and x y square. Okay. Okay. So now this is the important definition for any uh, polynomial, because yes, this is support of a polynomial. What is the definition of support of polynomial? So you can see we can write any polynomial like this: f of x y, that is equal to summation of ij to the power I y to the power j. Okay, maybe so x and y, they are different, maybe similar. That does not matter. But the important thing is the support of f, that is equals to the power of x, comma, power of y. So ij, I'm choosing this. For our polynomial, you can see this is our polynomial. You can see this is our polynomial. So the supports are 2 comma 0. So this is 2, y to the power 0. So 2 comma 0. Also 0 comma 2, 1 1, and 2 comma 1, and 1 comma 2. Just see. Yes, 2 comma 0, 0 comma 2, 1 1, 2 1, 1. Okay. So okay, now I want to discuss about the Newton polygon, the definition of Newton polygon. So just this is nothing. We are just putting the I mean support of any uh, polynomial, and we just connect to them to each other, and it will form a polygon that is called the Newton polygon. So you can see that this is just I'm here in this diagram. I'm just putting the value of support of the polynomial. So just putting the value up there, and in the next slide I'm just adding to each other, and we get this is form of polygon. So now this is interesting topic that is called the Minkowski sum theorem. So Minkowski sum theorem is saying that if f equals to gh, I mean polynomial, we can write it into two parts, that is gh. But also g and h both are also polynomial, so we can write this is the Newton polygon of f, that is equals to ng plus nh. Okay, so where the right hand side it denotes the Minkowski sum. This is called the I mean Minkowski sum. So this theorem explains why this I mean Newton polygon is useful for studying the factorization. So this theorem we were using in our paper with my supervisor. What we discuss about the Fibonacci sequences, and I mean we are putting the recurrence also using that equation or the polynomials in the Newton polygons and etc. So that's why. Okay. So now I want to discuss about the lower edge. Lower edge means that in the lower part, um, I mean the edge which is between in the and the lower part. Uh, for our cases, 0,2 and 2,0. This is the uh, lower edge of our cases. So you can see that is this is this is y-axis, so 0,2, and then this is x-axis 2,0. So this is our lower edge for here. It is situated in x-axis and y-axis onto the boundary. And also the important factor is that for our cases, the whole Newton polygon is situated in the I mean first coordinate, this plus plus coordinate. So now I want to discuss about the H polynomial. So H polynomials, the H polynomial is looking like 1 plus beta square t square plus 2 alpha beta t plus 1 plus alpha square. So it is irreducibility plays a very important role because okay, now I'll be telling that how we can do this thing. So the first from here we are just putting this value 1 plus beta square, that is a, and 2 alpha beta, that is b, and this is also, and we need to find the discriminant of polynomial, that is del, that is equals to, hello,
Yeah, we hear you.
hello,
Yeah, we hear you. We hear you.
okay. Yes, okay, sorry. Okay, del, that is equals to b square minus 4ac. Okay, so we just put the value here and we get our discriminant. So now for our cases we just simplify our discriminant like this. Now again there is a lemma that is very much important. So just see, that is if uh, our discriminant is not square in Q, then ET has no rational root. Okay, so now how we can prove this? So we know that Q is irreducible because rational root, it has exists a rational root. If it is irreducible, so uh, the discriminates is a square. Since del, and we calculate this and we cannot get that this is a square, because you can see that there is a 1, and we know that 4 is a square, and this should not be a square. So that's why it is irreducible over Q. So it is irreducible. Now the main theorem, that is, suppose alpha comma beta, that is belongs to Q, and our discriminant is not a square, then this is irreducible. Then fxy, that is irreducible over qxy. So how we can prove this theorem? Just basically what we did previously, and just we get using the Newton polygon and so on. So we just put the value of Newton polygon and identify the lower edges and find the discriminant. If the discriminant I mean if it is square or not, then we get that this is irreducible. So apply Newton Polygon irreducibility criteria, and we get the irreducibility of fx, okay, over qxy. Okay, so I'm choosing two more examples. Number one is that alpha beta both are 1. Okay, so we can get that is our delta is -1. So okay, so -12, which is not a square in q. So you can see that is another example, that is alpha equals to 1, beta equals to 2. So then delta equals to -4 into 1 plus 1 plus 4, that is equals to -24. So -24 is not a square, so fxy is irreducible. So I'm just thinking about no, but for these cases we cannot, maybe I don't know. I mean, for me, I cannot find any contradiction or looking like. I'm just thinking alpha beta, that is 0 for only, no, for 0. No. Okay. So now I want to discuss about the generalized Markov equation. So this is some misprint, that is okay. So how the Markov generalized equation is looking like. So it is it is x1 square plus x2 square plus x3 square up to n, and this is equals to n of x1 x2 into xn. Okay, so same thing is also applicable for here Newton polyhedra or so on. So we have to use these formulas on these cases, and we get some good solutions on generalized Markov equations also. I'm just trying to find these things and so on. So it has some application in Pell type equation. Pell type equation means that you know that Fibonacci sequences and some other cases. Also periodic analysis, algebraic curves, and arithmetic geometries, and etc. Okay. And the last, there are some open questions on there is a, you can find the Markov uniqueness conjecture, generalized Markov equations. Yes, I previously told factorization over finite fields and rational points on cubic surfaces and periodic irreducibility criteria, etc. Okay, so this is some references here, and also I told previously that I wrote some references in my slides and so on. Thank you.
Thank you so much. I don't know if you can hear me from here. I can get closer if no. Yeah.
Yes.
Yeah, it's okay. Sorry, I was at the other end of the room. So can you hear me?
Yes, I can.
Yeah, so we have some time for a couple of questions, maybe. I will repeat the question that someone asked. Any question, Anton? Okay, so I have a question. So if I follow correctly, the equation or the degree in particular that you start with plays no role whatsoever. So you could do this for any hypersurface in weighted projective space, regardless of degree or even, regardless of degree. Is that right? Can you hear me?
Yes, but I don't understand the question.
Yeah, so you did this for the Markov equation, but you could try this for any equation any homogeneous polynomial in three variables of any degree.
Not even homogeneous. The equation was not homogeneous.
No, you're right. Yeah. So you could try this for any polynomial in three variables. Is that right?
Yes, maybe. I mean, which slide? I mean, can you tell me?
Well, that's my point. That if I follow the argument correctly, there's no particular step that wouldn't work with a different equation, as long as it has three variables.
Yes, yes.
Oh, okay. All right. So I just wasn't sure. I thought maybe I missed it. Okay, I don't have a watch because my watch is my phone.
Exactly 55.
Okay, any other questions or comments?
There is something to check.
That's me.
Oh, that's.
I think it's me. Yeah. Okay, I have another one. At the beginning, you mentioned counting rational points. So can you count the number of rational points using this?
Rational point.
Yeah, you determine irreducibility, but at the beginning you mentioned as a questions. What are its rational points?
Yes. There is a paper, that is this paper. They discussed about we cannot find all the rational solutions of Markov equations and etc. But they were discussing about some solutions. I mean, some ideal solutions of the Markov equation in this paper, the saturation of Markov.
Okay.
So,
okay. Thank you. Any other questions? No? Oh, sorry. Yeah. You are going to repeat, or you are very loud.
Yeah, so at the beginning, you described a procedure of generating Markov triples with the C prime. So, kind of what can you get all the integer solutions like this, or do you need other procedures? How much does this cover for all the Markov triples?
Yeah. Okay. So you can see for these cases, I mean, I'm just generalizing these things. So C dash is looking like that. Also, it is B dash when this is 3A minus B. Okay. But here you can see that is A, or the X, A, that is all time same 1, or maybe some you can choose other constant, other terms, or etc. So this is a pattern. I mean, we can get some pattern and so on. I mean, you can see just A for here. You can see that is A. This is I mean, constant, one number, and B and C. C is also depending on A and B, but B is depending only on A. So these things we write here.
Okay, thank you. So maybe since I need some time to adapt the setting, maybe we stop here. Okay, thank you very much, Sashadhar. Thank you.
Thank you for